picking up then in section 5.6, instead of looking at two functions where we have an integral with respect to x and a function on top minus a function on bottom, we're going to be looking at functions where we would want to integrate with respect to y. So for example, I could draw my representative rectangle here, and as this rectangle slides along these functions from 0 to 1, the height of this rectangle, or the length, is going to change according to the right-hand function minus the left-hand function. And notice we have x as a function of y. So what we want to do here is we set up our integral, and we're going to integrate as y moves from 0 to 1 of the right-hand function, which is 12y squared minus 12y cubed, minus the left-hand function, which is 2y squared minus 2y. And then we integrate all of this with respect to y. Because as we turn our rectangles sideways here, and we have x as a function of y, the variable we're differentiating with respect to now becomes y. Y is our differential because if we applied the limit definition of an integral, we would be looking at the limit as delta y goes to 0. So that means you're integrating with respect to y. X has to be written as a function of y. You only want y's in the integrand. This is kind of turned on side what we've done previously in 5.6. Okay, and this is the first time we've seen integration with respect to y. The variable doesn't matter, and we let the graph of the function and what we were given dictate that we're using y's here. We could solve the same problem with dx's, but I would have to integrate. I'd have to break these down into 4 different functions, upper function, lower function, because I'd have to have y as a function of x if I wanted to use dx, and that's too much work. It's much easier to integrate this now. Setting up the integral is the hard part. Know that you can integrate with respect to y anytime you turn your representative rectangle sideways. Okay? So the arithmetic involved in solving this is still straightforward. We're going to distribute that negative, and then we get the integral from 0 to 1 of 12y squared minus 12y cubed minus 2y squared plus 2y dy. All I did right here was I distributed the negative. Now we look for like terms to combine, and we do have some like terms here. We're going to go ahead and combine those just to make the arithmetic easier on us at the end. So when we combine these two terms, we have the integral from 0 to 1 of what? I'm going to write 10y squared first. 10y squared minus 12y cubed plus 2y dy. Now, well, that looks ugly. There's a dy. We can integrate this one fairly easily using the power rule, right? So when I integrate 10y cubed, I end up with 10y cubed. I add 1 to the exponent. So this is 10 thirds y cubed. Let me write it like this. Or we could write 10y cubed over 3. It doesn't really matter. I'll write 10 thirds y cubed minus 3y to the 4th plus y squared evaluated from 0 to 1. Now, are there any questions about the mechanics here? No, it's 12y to the 4th over 4, and 12 divided by 4 is 3. That's the 12 over 4 reduced to 3. Okay? All right, so now we use the fundamental theorem of calculus, which says that we're going to plug in our upper bound, so that's going to give us 10 thirds times 1 cubed minus 3 times 1 to the 4th plus 1 squared minus, this is the upper bound minus the lower bound. So we have 10 thirds times y to the third minus 3y to the fourth plus y squared. And in place of our lower bound, we plug in 0. Taking care of the arithmetic now, this is going to be 10 thirds minus 3 plus 1. So that's going to be 10 thirds minus 3 plus 1 gives us minus 2. So that's minus 6 thirds because that's 2. We have common denominators we need to get. Minus, and then we get a 0 here because each one of these terms is a multiple of 0. So 10 thirds minus 6 thirds is, and that's our final answer. Any questions? Make sense? All right, let's look at this next problem. In example 7, you could either do a problem evaluating this using a dx, where you would have a representative rectangle that would be vertical. If you chose to do that, though, you'd have to break this into two integrals because we have one function on top on the left and one function on top on the right, and we'd have to break this into two different integrals. Or another option, we could integrate using a representative rectangle that was horizontal. Is it going to change what answer we get, whether we use a dx or a dy? It's not going to change the answer. So which one do you want to do? You know what? We're going to do both just to show that it doesn't matter. How about that? Okay? So the first time through, we're going to use two areas. Hang on a second, because I want to copy this picture. And we'll paste it over here. And I'll show you how I set up the problem based on which method I use. We're going to do the dx first. When I use the dx, I'm using a representative rectangle that's vertical. Now these representative rectangles in Cal 2 will become extremely important in the beginning as we start finding volumes of solids of revolution. So here I'm looking at a delta x. So I need my function to be y as a function of x. Are y'all okay with that? Does that make sense? So I have to break this into two different areas. Area 1 will be on the left, and it's going to use the blue function on top. Area 2 is going to be on the right. And this is actually the area of a triangle, isn't it? And I don't even need calculus to integrate this, but I'll use it. Okay, setting up the problem. We have the integral from 0 to 1, because x here, this rectangle, is going to slide along from 0 to 1, and that's where you determine your bounds, and it's based on what your differential is. This is a dx. And we integrate x squared from 0 to 1, plus, if I solve this equation for y, I get y is equal to 2 minus x. So this is going to be the integral that goes from 1 to 2 of 2 minus x dx. So when I find this first area, I'm going to integrate this first area, and I end up with 1/3 x cubed from 0 to 1 plus 2x minus 1/2 x squared from 1 to 2. Any questions about how I integrated? Where any term came from? Okay. It's the screen.
I'll look at that.
I can move this all day long and it won't change that. Sorry. If somebody's tall, they could try to turn that. I'm not going to do it. Zishan, you want to turn? We're having trouble with the monitor in the classroom. Okay, look over there. That one's right. Okay, so now using the fundamental theorem of calculus, when we plug in the 1, we're going to get 1. Am I okay cutting some corners here and just saying that this is going to be 1/3? Because when you plug in your upper bound, you're going to get 1 minus 0 and that's just 1. So that we end up with 1/3 here. And right here, when we plug in our upper bound, we're going to get 2 times 2 minus, oops, wrong color, minus 1/2 times 2 squared. This is the upper bound, minus the lower bound, and that's going to be 2 times 1 minus 1/2 times 1 squared. So this is going to be 1/3 plus, that's 4 minus 2 is 2, minus 2 minus 1/2 is 3/2. So this is minus 3/2. So we got to get a common denominator. Our common denominator is going to be 6, so this is 2/6 plus 12/6 minus 9/6. So 2 and 12 is 14, minus 9 is 5/6. Is that correct? You are checking my arithmetic, right? We all know that's not my favorite thing. Okay, this is solving by using a dx. In the next problem, we're going to solve using a horizontal representative rectangle, and now we're going to integrate from where to where? 0 to 1. Let me get this rectangle here. Because the y's are going to, this is not playing nice. The y's are going to go from 0 to 1. So when we set up this rectangle, we're going to integrate from 0 to 1. And we do the right-hand function minus the left-hand function. But because this is a dy, because we have a delta y here for our width of the rectangle, we need to write x as a function of y. So this is going to be x equals 2 minus y. How do I solve for x here? X is equal to the square root of y, correct? So this is the left-hand function minus the right-hand function. Agree? So far, so good? Larger values on the... I said that backwards. I wrote it fine, but my lefts and rights got confused. It's the right-hand function minus the left-hand function, because numbers to the right on the number line are larger than numbers to the left on the number line, and we want a positive value here, so we do right minus left. Okay, so solving this integral then. We have the integral from 0 to 1. We can just apply the power rule straightforward, can't we? When we integrate 2, we get 2y minus 1/2 y squared minus, because these parentheses aren't really necessary, add 1 to the exponent. So that would be 2/3 y to the 3/2. Evaluated from 0 to 1. Agree? Okay, plugging in our function values. When we plug in our upper bound, we're going to end up with 2 minus 1/2 minus 2/3, because 1 raised to any power is 1, and 1 times anything is just that anything. So there's our upper bound, minus the lower bound is just going to give us 0, right? So look at what we have. We have 2 minus 1/2 minus 2/3. So this is going to be, our common denominator is 6. This is 12. 6 minus 3. 6 minus 4, 6. And negative 3 minus 4 is negative 7, plus 12 is 5, 6. Notice the method that we used did not change the outcome. The area is still the same area. But whether or not we used a dy or a dx didn't change that area. And it was just as easy to solve for x in terms of y as it was to solve for y in terms of x. And we got to use only one integral here, which made life easier, I think. So look at the problem whenever you're asked to find the area of a bounded region and decide which would be the best way to set this up, as a dy problem or a dx problem. Question, do you see how to determine when to use a dy or a dx? Yes? Yes, 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 yes. Thomas? Taylor? Okay, looks like we're all 100%. Okay. The method doesn't dictate the outcome. Just like if two different people start out at point A and they want to get to point B, one may take the right way, one may take the long way. Right? So, all right. Example 8. Find the area of the region in the first quadrant bounded on the left by the y-axis, below by the curve x equals 2 square roots of y, above left by the curve x equals y minus 1 quantity squared, and above right by the line x equals y minus 3. They were kind enough to graph this region for you. Don't count on that always happening. Now, with one this complicated, trying to determine the region, I would probably give you the graph. But I could have just as easily not given you the picture, and you would have had to have drawn the graph or use your calculator to graph, which can be a problem if you have x as a function of y, because your graphing calculator only allows you to graph functions, not relations. Okay, so you're still going to have to know how to graph to a certain extent. Now, when we look at this problem, what's the first thing that goes through your mind? Besides, oh crap, I don't want to do this. Okay, what's the second thing that goes through your mind? We have 3 different functions, but what are we asked to find? The area. So we've got to determine, do we want to integrate with respect to y, with respect to x? If so, where do we draw our line, and how do we set up our functions and all that stuff, right? So which do you think would be better, a dy or a dx? I really don't know. Look at the functions you're given. You're all given x written as functions of y. Because of that, I would probably go with the delta y, because it involves less algebra for me. I don't have to solve these equations for y in terms of x. So because of the way the functions are written here, we're going to opt to go with a dy. So that means that our rectangles here are going to be horizontal, right? So that we have a delta y, our representative rectangles. So that means that I'm going to take the right-hand function minus the left-hand function. The first thing you might want to do now is determine what are these points of intersection. How do you determine these points of intersection here? Well, this point right here is where the graph x equals 3 minus y and x equals 2 square roots of y intersect. So why don't we set 3 minus y equal to 2 square roots of y and see if we can solve this equation for y. And that'll give us a point of intersection. Okay? So the first thing I might want to do is actually square both sides to get rid of the square root. So let's try that. Let's square. So that gives us 9 minus 6y plus y squared equals 4y. What type of equation is this? Quadratic. So when we solve this quadratic equation, we end up with y, not plus, y minus 1 and y minus 9, because that'll factor. So guess what y is equal to here? 1. Oops, y is 1. X is 2. This is the point 2, 1. Now, you could probably tell that just by looking at the graph, but I wanted to make sure you understood the process of how to find points of intersection if they're not clearly denoted, because sometimes there may be square roots and stuff in these answers, and you've got to give exact answers. What about this point of intersection? How do we find this point of intersection? We're going to look at y minus 1 quantity squared, and we're going to set that equal to 3 minus y. Okay, so we FOIL this out, and we're going to get y squared minus 2y plus 1 equals 3 minus y. This is a quadratic equation, so we're going to set this equal. This is minus y minus 2 equals 0. So we factor minus 2 plus 1. And we end up with y equals 2. Right here, it does look like y is equal to 2, so this is going to be the point 1, 2. Once you know y, you can get x. All right, so now we've got to set up all of this, by the way, was how we find our points of intersection. I'm going to need more room to work here. All right, so we're going to set up an integral now. We're going to integrate